Voilà, c'est bien. Il est midi.
Hmm.
Est-ce qu'on va continuer? Est-ce qu'on va... je vais commencer la présentation de notre conférencier, le docteur Aldo Zollo, du département de physique de l'Université de Naples, Frédéric II. Alors d'abord, hein, Frédéric II, c'est quand même une université du fameux roi de Sicile, Calabre et du sud de l'Italie, le roi qui a accueilli les savants musulmans au XIIe siècle. Donc c'est un signal. C'est un signal de... Alors, Aldo, bon, je crois que je vais le présenter, mais l'a présenté à Aldo Zollo. C'est c'est peut-être inutile à mon point de vue, mais je vais le faire quand même. Aldo a eu son premier diplôme de physique à l'université de Naples en 1983, parce qu'il est originaire de Naples. Et il a préparé donc une thèse de doctorat en sismologie à l'université de Paris 7, en France. Et nous étions ensemble à l'Institut de physique du Globe de Paris, ensemble aussi avec Mourad qui est avec nous aujourd'hui. Donc, Mourad Bezroud. Euh, et donc, Aldo s'est intéressé d'abord à la sismologie, surtout la sismologie de la source. Et ensuite, il a poursuivi donc ses recherches à la faculté des sciences donc, de l'Université de Naples, Frédéric II. Et depuis, donc, il a continué ses recherches sur non seulement la source, mais les processus les signaux sismiques, la physique de propagation des ondes, euh, euh, et durant les dernières années, dernières décades, il s'est occupé de l'alerte sismique, de l'alerte sismique. Voilà. Donc, c'est ce qu'il va nous présenter aujourd'hui. Alors, j'aimerais juste dire une touche comme ça un peu amicale, c'est que on s'est retrouvés tous les deux, tous les trois, Tani, avec Mourad, à Paris, à l'Institut de physique du globe de Paris. Et au début, on ne se connaissait pas, mais on était comme ça un peu, on se regardait à distance. On se disait, bon, ce chercheur qui est venu de Naples, c'était un petit peu exotique pour nous. Et finalement, donc, on est devenus de bons collègues, d'abord, hein, de bons collègues. On échangeait beaucoup en sciences on est restés amis jusqu'à maintenant. Donc, c'est un privilège et un honneur pour moi de
Hmm.
présenter Aldo. Je donne la parole à Aldo. Voilà, merci.
Merci beaucoup, Mustapha. Merci à tous les participants. Je tiens à vous remercier parce que pour moi, c'est un honneur de pouvoir présenter mes travaux de recherche à une audience aussi importante. Et voilà, donc une question que je vous pose, est-ce que, moi j'ai préparé ma présentation en anglais, est-ce que vous pensez que je dois la faire en anglais ou bien, vu que comment vous préférez?
Ouais, je pense en
Comment-
anglais, ça ira très bien.
Okay,
In English.
okay, that's perfect. Okay, so I will start my talk today. The title is Impact-Based Earthquake Early Warning. And I will try to present you the basic concept and example of its implementation and use, in particular the application that we at the University of Naples are developing in these recent years. So, as you probably know, the earthquake process uh, involve very large and different time scales. And typically we go from the decades before the earthquake occurrence with long-term hazard mapping, then years or days. And here, this is the big issue of earthquake preparation, possibility to identify and detect precursors. This is a challenging topic in seismology. Then once the earthquake is occurred, we have an earthquake early warning in the seconds that follows the earthquake occurrence. So first concept is that earthquake early warning is not earthquake prediction, but the event is already occurred. So what we are predicting actually is the impact of the earthquake because the earthquake produce different waves at the origin, and the very first waves, the P waves, propagate at a faster velocity, and we can benefit of this velocity, of this speed, to have information about events in real time. Then in the minutes after the events, I will say also the hours, shake map are built and they are of support to the emergency actions. And then in the scales of days and months, depends on the magnitude of the event, we have the aftershock hazard, especially in countries like Italy or in several other countries of the Mediterranean region. The earthquake hazard is the aftershock hazard, sorry, is very important because main event can trigger the secondary rupture of on faults that can have a similar extent of the main shock. And we call them segmented rupture. We have many examples, especially in Italy, since the Friuli earthquake in 1976, Irpinian earthquake 1980, etc. Earthquakes generally do not occur alone, but similar size event can occur. So there is an important issue, which is the aftershock hazard. So earthquake early warning is substantially an idea that grounds on development of high performance technologies, sensor network, telecommunication, and broadcasting of the alert. The objective is to identify as soon as possible the ongoing earthquake and provide a warning to distant sites, so sites which are distant from the earthquake occurrence, before that the ground shaking reaches the target sites. You see here on the right column a time scale. So you have earthquake occurrence, then waves propagated to the network at the surface, and so we have a kind of blind zone. And finally, as soon as the first waves are collected and analyzed in automatic way, information about the earthquake characteristic can be obtained and so transmitted at the sites that need to be protected. But the same network, actually, this is the case for many regions in the world, can be used for estimating the earthquake impact in terms of strong ground shaking and macroseismic intensity, typically in the 10 of minutes, half an hour after an earthquake. These networks provide what we define the shake maps that are the representation on the surface of the earth of the area that suffered the highest intensity during the earthquake. And this tool is really very, very important to quantify the earthquake impact in terms of losses, lives, damage to the buildings, but also to plan rescue actions and to set the priority where to intervene after an event. So it is really a tool that is useful for the society. what are the basic concept of earthquake early warning? Actually, we base almost all systems grounds their functioning on the measuring properties or parameters along the P wave. And these parameters can be the amplitude of the P wave or the frequency content of the P wave. Sometimes we call it period, characteristic period, predominant period. And so these two informations, amplitude and frequency, are used to predict, essentially using empirical relationships, the amplitude and frequency content of the late arriving wave, the S waves, or the surface waves that are causing the damage in general. So looking at these seismograms, you can understand, I think, that the time between the arrival of the P wave and the S wave at the same sites represents what we call the lead time. So the time available for any safety actions. During the year, I would say during the last about 2 decades, there have been developments worldwide on early warning systems. I can broadly classify the earthquake early warning systems in 2 categories. The first is called the network-based or regional, in the sense that they use the information from a seismic network located in the region where the earthquake occur. Then the network using parameters of measured on the P wave estimates the magnitude and the location of the earthquake, and using 2 parameters and previously known attenuation relationship, one can predict the peak ground motion in the wide area around the epicentral region. That is the network-based or regional approaches, which is the largely most diffused early warning system worldwide. On the other hand, we have the on-site or threshold-based method that indeed is based on the recording of the P wave at the target that we want to protect. Essentially, what we have observed here. So we profit of the time delay between the late arriving strong shaking phase relative to the first shaking phase. Nowadays, both systems have advantages and limitations. So nowadays, the global idea, and in the example that I will show you later, that is the case, the global idea is to integrate these 2 approaches. So to build a combined early warning that is based both on regional and on-site systems, so threshold-based systems. One important parameter that is used to assess the performance of early warning system is the warning time. That means what is the first time that an alert can be issued from a typical early warning system. So to illustrate this concept, I plot here the classical travel time curves of the P wave and S waves. This is very general classical travel time curves. On the y-axis, we have the arrival time. On the x-axis, the epicentral distances. This horizontal line at about 6 seconds represents the minimum time that a typical local network needs to get information about the earthquake size and location. I will say 6-7 seconds. And so any distance that corresponds to this time, typically 20-30 kilometers, is called the blind zone, because no information can be raised, no alert can be raised to this distance. it is clear that if we want to restrict the blind zone to a smaller distance, we have to build dense, very dense networks. This is represented here, a typical case of the density of a network in Italy, for instance, where we have approximately one station every 30, 50 kilometers all over the Italian territory, the part of the Italian territory where we expect that the earthquake occurs. So the warning time is the time where the first P wave collected by the network are able to provide the alert. Then the waves, the S waves propagate along the crucial volume and reach the sites. And as you can see with this graph, you can define an interval between the arrival of the S wave and the warning time. This time interval is called lead time. And this is a very important parameter that characterizes early warning systems because, of course, we need large lead time to do actions for emergency. So the best system is the one providing sufficiently large lead time. They are typically of the order of seconds to tenths of seconds, depends on the distance where the target sites are located. In general, network-based early warning systems provide fast and accurate source parameter determination, but they are less reliable in the potential shaking estimates. This is one of the reasons why we nowadays tends to combine the two approaches. Here is a map that I took from a paper published in 2019. The situation has not much changed since 2019. The early warning development all over the world. We distinguish cases where the early warning systems sent the alert to the public, which are the violet rhomboid symbol. Then alert sent to a selected number of users, circles, and then stars indicate the sites where early warning is still under testing and not operational indeed. So you can see that indeed almost all regions in the world, they are experimenting and using earthquake early warning systems. In Japan, as you know, there is a big experimentation that was born in the 1960, in the year 60 of the last century, with first application to the railway, and then now the Japan Meteorology Agency is running and operate this early warning system for the entire country. In Europe, actually, no operational early warning systems is ongoing, except for Romania, where in Bucharest the alert is sent to a selected number of users. In Turkey, I don't know because I have no precise information. I know that during the last event, the events of February 2023, no early warning system was ongoing. What we can do actually with these alerts, essentially, there are two possibilities to use the early warning alert. One is for individual action. So the individual person or people that receive an alert take an action to protect himself or herself from the potential damage that is ongoing. Or most of the cases, indeed, early warning systems are linked to automatic actions. So the alert pilot an action that automatically produce the halt of trains, the shutdown of electricity, the halt of lift in buildings, and so on. So you see here the general environment of applications for power, industry, construction, transportation, response community, personal protection. I will say that, that will be one point of my conclusions, that although there are a number of studies I mentioned here, one from James Golds in 2002, where the potential of earthquake early warning for all these kind of application are studied and simulated and so on. In general, there is no such a wide application in the industry actually of the and use of the earthquake early warning alert. I will show you our work with the high-speed railway company to see one of these effective use. I don't know how to remove this banner above. Okay, I will continue with that. So now, what is the state of the research where we are going? Actually, as I say, there are different approaches that are developed along the world, but the next future research will be probably addressing these two specific topics. On one way, since rapid response information is very important, we want to develop new and advanced monitoring systems capable to work in real time, that are able to operate both in early warning and rapid response mode, so that in an ideal time scale, like the ones that I show here in this figure, we, as the earthquake occur, we first provide the early alert and then come to a more refined analysis of the signals in order to get a best evaluation of the impact through the shake maps. In this transition, very important is the possibility to characterize the earthquake complexity in such a way that this complexity is included in the model, and so it can be used to get a more refined prediction of the impact. The other aspects that is, to my opinion, the next future application of the earthquake early warning is to design systems that are tailored to specific applications. If we want to use for nuclear plants or highways or train, we need to adapt our method to interface this method to the specific control systems that are developed in these environments. I will show you the example of the high-speed company that, to me, is very clear that we should go in that direction. And this is also a need because today earthquake early warning method needs to be demonstrated with successful example, and a true demonstration can happen only if we demonstrate that the system is able to control action that can save people, that can protect buildings, can protect infrastructures. So in the framework, so the title of my talk was impact-based, because actually the most of methods can be classified in these two categories, source-based and impact-based. And nowadays, we are more working in the direction of the impact-based approaches. What does it mean source-based? That's exactly what I explained before. The aim of the early warning system is to fast determine the location and the magnitude of the event, so characterize the source, even using a very simplified model for the source. It is a point source. We get location and magnitude, and then we use these two parameters in the attenuation relationship that nowadays engineers calls ground motion prediction equations, and so get the prediction of the peak ground motion. So actually the early warning systems is aimed at characterize location and magnitude of the event. A number of softwares and algorithms have been developed, the ones that is running at the Japan Meteorological Agency, for instance, the one that is running at the USGS, the Shake Alert, our original Presto method, and virtual seismology in ATH, they are all methods that are based on this idea to get a fast determination of the source parameters. But the impact-based approach is instead independently on the magnitude and location of the event. Can we have a future peak ground shaking from the recorded as P waves? The idea comes more similar to what we do in meteorological prediction, where we use the data that are collected now to predict the evolution of the clouds and rain wavefront, etc. So here, can we use the data that are collected at the dense array? You see here, for instance, the array in Japan that are very dense, to predict what is going on in the next future, in the next distance, without making use of the source location information. In this direction, a number of new methods are developed. Okay, the main advantage that we don't incorporate in our method the uncertainty that is related to the estimation of the magnitude of the event, essentially. And the magnitude of the event is based on the analysis of a relatively short time window. So a clear underestimation of this magnitude can be provided by the use of such a short time window. The method that we have developed at the University of Naples that has the aim to provide an alert based on the shaking forecast or definition of potential damage zone is in the mid of this source and impact based, because we partially use the earthquake source information, but basically use the P-wave information to project this information into the late arriving and possibly damaging S waves. The concept of this method is represented in this slide. The idea is to use the currently and time evolving measurements of the P wave recorded at stations that are triangles in this figure here, and the value of predicted peak ground motion at circles through ground motion prediction equation. These two data are combined to map what we call the potential damage zone, that is the area delimited by a user-defined level of intensity or peak ground velocity. So, if, for instance, if the intensity threshold is 7, this taking the relationship determined for the Italian territory corresponds to a PGV of 6.4 centimeters per second. And these values are indeed used for the INGV National Institute of Italy of Geophysics and Volcanology for the calculation of the shake map. So taking this threshold, we could track as a function of the time from the very first P-wave recording the shape of this area, and so alert all sites that are within the area and outside the area on the ongoing earthquake. Here we see more precisely if you have a network of stations and a spatial grid of virtual nodes. As the first P wave is detected at the closest station, we get a preliminary estimation of the earthquake location and the magnitude, and then we combine, as the time goes on, the PGV predicted by the recorded P waves at the stations and the PGV predicted by the ground motion prediction equations in the area. Here, in this plot here, you see a diagram that shows that the peak displacement that is measured in less than 3 seconds on a P wave is relatively well correlated to the PGV. And so we used statistics that use this correlation. The same can be demonstrated, holds for peak acceleration and peak velocity that is measured on the P wave time window. So as the time goes on, successive measurements are done on increased time windows, and new station recordings are acquired. And so finally, the shape of this potential damage zone, which is the red area in this figure, is better and better delineated. And so at each time, we can update the alert and provide information about where is the area where the maximum shaking is expected during the earthquake occurrence. So after this broad general introduction, I want to propose you two case studies that are part of the research of my research group here in Naples. One is about the retrospective performance analysis of this system that I showed you before for the 2023 Turkey and Syria event, main shock of moment magnitude 7.8. And the other case study is indeed the design, development, and prototype implementation of the first earthquake early warning system for high-speed railway in Italy. So coming to the Turkey-Syria earthquake, we know that on February 6, 2023, a doublet of very strong earthquake, magnitude 7.8 and 7.6, occurred with a time distance each other of 9 hours. They struck the cities of Pazarcik in south-central Turkey. Both events are associated with a rupture occurred along the eastern Anatolia fault systems. And as the figures show here, a large area was affected by an intensity greater than 7 plus here. That is classified with a shaking of very strong to violent extreme. So the damages and were really, this was a really disastrous event. This event was the main shock of this, and also the secondary event were characterized by a complex rupture process. In particular, the main shock triggered on a secondary fault of the East Anatolian fault system, the Nurdagi-Pazarcik fault. Then the rupture propagated about toward the north direction during the very first 20-25 seconds from the earthquake origin, and then a secondary rupture triggered bilaterally towards south for a total rupture length of about 350 kilometers. So from 200 kilometers north of the junction zone between the original NPF fault and the S fault and the East Anatolian fault. This is one of the many models that have been produced after the event. It was published on Seismica by Merger et al. But essentially, the nature and the way that the rupture propagates is almost identical in all the proposed models. So the rupture was really very complex here. So we analyzed the data from the very dense strong motion network that is owned and operated by the AFAD agency in Turkey. You see in this plot the distribution of stations that are really very dense, actually around the fault. A number of them were located along the East Anatolian fault. And analyzing in an increasing P-wave time window the P-wave signals, we were able to get a time evolving estimation of the magnitude that you can see from this plot. All the gray lines represent the story of the moment magnitude determination at each individual stations, while the blue line is the average estimation. You can see that we started with an underestimation of the magnitude, and then the magnitude that is a P-wave magnitude slightly increased to reach a stable value at about 40-50 seconds after the origin time. Since the magnitude determination depends on the error on the earthquake location, you can see in the top plot the evolution of the earthquake location as a function of time. And we see that within the very first 20 seconds, we get a quite stable earthquake location determination that is very consistent with the same determination which have been done by the standard agencies using offline and not real-time data. So we get a slow convergence to the final magnitude value from 6 to 7.5. So there is an underestimation because typically P-wave provided a slight underestimation relative to the S-wave. And we interpreted this slow convergence as the effect of a low energy release during the very first 40 seconds for the earthquake, as it has been inferred from the moment tensor rate, the moment rate function of this event. So the scope of this paper was to evaluate the performance of the system. So the performance of a system can be evaluated in terms of not only the time of the warning and the lead time, but also the quality of the impact prediction. So how many sites have been well predicted in terms of intensity and so on. The top figures here show for two specific thresholds, intensity 4 and intensity 6, the number of successful alert. So when the predicted intensity was higher than the threshold, and in effect, the observed intensity was higher than the threshold. And the other two cases are the missed alert in red, and the yellow in the yellow are the sorry, in the missed alert in yellow, yes, and in red, and in yellow we have the false alert. And so we can see, comparing the results for threshold intensity 4, threshold intensity 6, that since the very beginning, the percentage of successful alert are much higher than false and missed alert in the case of the lower threshold. So if we increase the threshold, then we are in the case of having more not good alerts, so more missed or false alerts. And specifically, what we see, if we want to have a good ratio between successful alert and missed and false alert, we have to wait a long time from the beginning. The bottom figure are interesting because with the green point, we plot the time at which the predicted alert overcome the threshold, the predicted intensity overcome the threshold. And the red is the time at which effectively the observed, measured intensity overcome the threshold. And so we can see that moving from 0 kilometer distance to 300 kilometer distance, there are a lot of sites where we can have between 10 and even 50 and 60 seconds of lead time in the case of the lower threshold, allowing for actions in this time. So from few seconds to 50, 60 seconds, depending on the epicentral distance. So what was interesting that we observed in our simulation, our study, is that if we map the potential damage zone or the strong shaking zone as a function of the time, this region well delineates the geometry and the extent of the rupturing fault. I will show you an animation and then I will comment it. So we start from 9 seconds, actually. That is the time that the first P wave was recorded at the first station. You can see, unfortunately, I cannot get out of this bar here. I don't know how to take it out, but you can see the evolution of the potential damage zone. Here we are about 30 seconds from the beginning. And then you see, I can replay again to be. So at the beginning, the rupture stay along the gnarly fault, then propagate to the north during the first 30 seconds, and then started to the south. And what is really interesting here is that these maps are built by using the predicted PGV from the P wave amplitude. So P wave seems to be very informative about the. Excuse me? Excuse me? Okay. So this is interesting to show how this method is very efficient into delineate in time the space-time evolution of the rupture. And in this way, it is able to incorporates in the prediction the complexity of the earthquake rupture process. So the second example is about the earthquake early warning system that has been developed in a joint project with RFI, that is the railway company in Italy. Initially, the idea was to develop a prototype along about 200 kilometer segment of the high speed railway going from the cities of Naples and Rome. And we developed the system from the scratch. So we implemented all the infrastructure for monitoring, including accelerometers, telecommunications, and so on. What was the objective of this system? What is the objective of this system? Because now we are in the stage after 4 years of implementation, we are in the stage of making it operational. The objective was to declare and dispatch the alert to the control room of the traffic, of the train traffic, activate those devices that regulate the traffic, the train travel, and then trigger the stop of slowing down of the train. And finally, what was very important for them, to declare the end of alert and to map the sites along the line where the pigment motion exceeded a threshold. That was very useful. That is very useful for all the operations that are done after the event occurrence and the stopping of the railway traffic. The system is very complex. Indeed, it is a system of systems. We have the sensor network, we have the telecommunication with a dedicated fiber systems, then the earthquake early warning platform that is designed to automatically be linked with the system of train blocking actuators. So any of these systems has its own maintenance, its own system to monitor the functioning of any components and so on. So there is a complex architecture that makes each system talking to each other in order to be really effective. So in this case, the point was not to estimate the magnitude of the event or to estimate the impact, but was to identify the segment of the railway that is likely affected by a strong shaking. So the output of this early warning system is actually the coordinates of the eastern point of this segment along the railway. We use it essentially an on-site, combined on-site network-based system with the observed P wave, the region along the line is identified, and this is the region that this information is passed through the control systems that activate the train braking systems. This is an overview of the different components. In the 1 and 2, we have the early warning system. Then we have the systems of the train actuators, and we worked with several companies to develop new technologies for all the devices that are set along the railway to control the traffic of the trains, actually. So even in this case, the problem was to set up an environment for evaluating the performance of systems, saying that we don't have any earthquake recorded at the actual network that have been developed. So what we did is to imagine a virtual train line running along the Apennines, and used it was in central Italy, and used the earthquakes recorded by these stations along the line to simulate the occurrence of event along the line, and then to study the performance of the systems. I don't have the time to go much into detail. I think the best is to show you a simulation like this. On the left, you will have the real-time streaming of the waveforms at the different stations, and on the right, you will have the black line, where the red line that represent the segment to be alerted, it is shown as a function of the time. Let's go on with the simulation. So at this time here, the earthquake is not yet occurred. Now we have earthquake detection, and you can see with this yellow region along the seismogram, the event has been detected at these stations along the line. And initially you can see a segment red that is put on the line. And as the time goes on and the new P wave is recorded along the line, you see the red segment expand. The simulation is for the largest event of the Central Italy sequence. So the red segment is quite long because the magnitude of the event was very large. So at the end, you see in few seconds, you get the representation of the part of the line that could be affected by large intensity. So one point was that was asked to us was to understand what is the effective use of this system for trains running on the specific railway. And to do that, we studied the impact of all possible events occurring in the Apennines based on the historical catalog along the given railway line. And we inferred an empirical relationship relating the length of the segment along the line as a function of the magnitude of the event and the distance of the event from the line itself. This was important because it was asked to understand how much this system would be effective in this operation during the years. What is interesting is that this is a railway line, a railway that is very densely passed by trains. So we have a very high number of trains passing through this segment of the line. And so taking into account the relationship that I explained before, we were able to estimate the average number of trains traveling within or outside the alerted segment of the railway, depending on the magnitude of the event, depending on the estimated return period. In summary, we can say that for almost all the estimated alerted segment of the length, and considering the slot of time during the day between 6 and 10 and 2023, we could estimate that the percentage of train that could be alerted being outside of the dangerous segment is always favorable as compared to the train that are already within the segment when the alert occurs. So we have two typical actions to be done: prevent events to enter in the alert segment once the alert is received, and for the trains that are within the alert segments to slow down their speed to value of the speed which are not dangerous for the train. So in conclusion, for this application, we say that the development of the early warning system for high-speed railways in Italy is really now a strong and challenging scientific and technological issue, because we have short epicentral distances and short lead times, and a high impact of potential false and missed alarms. These systems, as I try to illustrate to you, is perfectly tailored to user needs. And for this, we needed to be interfaced with the control system of the railway. The important fact is that the experience that we gain with this prototype development lead the company to expand these systems in next future to the whole national network. So this is actually the conclusion of my talk. I thank you for the attention. I would say that after about 2 decades of experimentation worldwide of earthquake early warning systems, both methods and technology, they showed the systems to be robust and reliable and ready for providing alerts, both automatic and individual. There are, however, major limitations. One is about the legal issues related to the use of the earthquake early warning. So in practice, who is responsible for an alert that is given by a machine? And if this alert is false or is missed, then there is the big issue of training of population to the use of this system to be able to act very rapidly after an alert. And finally, as I show you, an effective early warning system must be tailored to the user-specific needs and interlinked with the system actuators. There is another message I want to say, that nowadays, early warning and rapid response can use the same dense, advanced real-time monitoring infrastructures of earthquakes. And so we are ready to have a system that is able to move from the early P-wave-based shake map to the final S-wave-based shake map in seconds or minutes. This information is very, very important to reduce, mitigate the earthquake impact, and also to support the civil protection for all post-event emergency safety actions. So thank you for your attention, and I'm ready to hear your questions and try to
Yes.
answer.